Good morning, everyone. Today we will have our third lecture regarding the design of compression members. In the previous lectures, we discussed about the main equation for evaluating the resistance of a compression member, which is CR equal to phi multiplied by the area multiplied by the F yield divided by 1 plus lambda to the power 2n all raised to the power 1 over n. And we talked that we are mainly talking about lambda, which is function in Fe, and we mainly focused about the calculation of Fe, and we solved an example last time about the evaluation of Fe of doubly symmetric section. In today's lecture, we will focus about some new aspects. First, what will be the case if we have different buckling lengths, and also we will look into the case where we have a built-up section. And finally, what will be the case if the section does not satisfy table 1, how to can still use a very similar equation with a little bit of a tweak. So we will start just by a brief introduction about the buckling lengths. I know that I already talked about it in a previous lecture, but I will just refresh your mind. So we will go with the first case where we have our compression member is like that. There is no lateral constraint in anywhere along the length of the column. So obviously the buckling length will be just the entire length of the column. One thing I would like to first remind you about, it is the naming of the axes. So we agreed on that usually axis X, it is the one perpendicular to the web, and axis Y is the one parallel to the web. And no matter how the column is rotated, those axes naming will still remain the same. And also we talked about what type of beams will be limiting the buckling lengths. So we mentioned that whenever the beams are oriented in the X direction, so they are limiting the buckling and the buckling length in the opposite direction. So for example, if the beams are oriented with the x-axis, they will be shortening the buckling length in the y-axis and vice versa. So it is exactly the case in the second example here. So let's say if we have our column oriented in that way, which is the common one, and we have some beam, either one or two, limiting the buckling length in the middle. So as we can see here, this beam is kind of in line with axis X. That means that it will limit the buckling about the Y direction, and you can even see it. So if that column would to buckle in that full length, it will be prevented by the existence of that beam. This is why the buckling length will be just those distances rather than having the full length. However, if the column would to buckle in the perpendicular direction to the beams, it will be fully free to buckle with its full length. However, if we rotated the column in the third case that we have over here, then Lx will be the one that will be shortened, because as you can see here, this will be now axis Y. So since it is parallel to the beam, so the buckling length will be limited about the x-axis. So Lx will be the one that will be shortened. It is worth mentioning also, if we have a column like that, and I am drawing an elevation view, obviously if the column is constrained in the middle, so that will be the buckling length. So if the column has a full length of L, so the buckling length will be L over 2. However, it is worth mentioning what will be the case if you have unequal lengths of the column in between the constraining beams. So let's say if the beams are located over here, so we have, let's say, a distance of 2 meters here and 4 meters here. In that case, both will be buckling lengths, but obviously the bottom one will be the governing one because it is the larger buckling length, and this will may cause the failure in the column. And if that column would to deform, it will just deform in that shape. Okay. So that will be one of the concepts that we will tackle during today's example. We will go right to the example. So in the example, we are required to evaluate the compressive capacity of a column, similar to the previous example. But this time it is a built-up section, not a fully built-up section, because like a fully built-up section can be named for the section that is made of a couple of plates and you are connecting flange to web to flange based on this built-up section. However, in that case, we still have a hot-rolled I-beam that I'm hatching over here, but I am adding to that an additional plate, This plate has a number of advantages, and it's important to understand those advantages. First, it will be increasing the inertia about the x-axis, obviously, and y, but mainly the x, of course. And accordingly, the Rx will be higher. So in that case, we are expecting the CR to be higher. So in the exam, if I give you an example similar to that without the plates, and then I told you what will be the capacity, or how do you expect the capacity to change if we add those plates? So definitely the compressive capacity can be boosted up by adding those plates because they will influence the inertia, and the inertia will consequently change the Rx. Okay? So that's one of the advantages, actually. One of the other advantages, sometimes if the flange does not satisfy table 1, so the flange does not satisfy table 1. So table 1 in that case will exhibit local buckling. So one way of fixing that, or either for the web, by the way, but in our case we added plates to the flange, we can actually put 2 plates like that. When we add those plates either to the flange or to the web, they will prevent the buckling of the flange because they are welded to it. In that case, and this is important, we will check the local buckling of the plate, not the flange. Why? But we used to check the buckling of the flange. Yes, we used to do that when they are only relying on their own, but if they are supported by a plate, in that case, we just check the local buckling of the plate. If the plate is satisfying table 1, in that case, we don't need to check the element of the section that is connected to the plate. So in our example here, if the plate is connected to the flange, in that case, we only need to check the local buckling for that plate, not to the flange, but we still need to check the local buckling for the web. Okay? And we do acknowledge that those plates will increase the CW and J, but in the example we are mentioning that ignore the contribution of those 2 plates to CW and J. And keep in mind also that those plates will increase the cross-sectional area. So in the equation of the CR, I'm not going to write the denominator, but it is area multiplied by phi multiplied by the area multiplied by the F yield. The cross-sectional area actually will increase because you actually added an additional cross-sectional area from the area of those 2 plates. So actually the first step is to check the local buckling, and after that we will consider as well what will be the properties of the combined I-beam with the 2 plates. In that example as well, there is an elevation view of the column. So the column is pinned obviously like that, and the column is supported in the middle. But keep in mind, based on our discussion, that will limit the buckling length only in one direction. Now, if I draw the I-beam in that shape, and we have some dotted lines like that, do we expect that the I-beam looking like that or looking like that? Obviously, it would be similar to option 1, but not option 2, because we have those dotted lines representing the web over here. In that case, we understand that this will be the orientation of our I-beam. So since we were able to draw the orientation of the I-beam, we can draw the x-axis and the y-axis. Now, if we look here, we will find that this supporting beam is in line with axis x. And we already explained that whenever the beams are oriented with the direction x, then they are limiting the buckling length in the y direction. So in that case, Ly will be equal to 2.5 meters, while Lx will be the buckling with the full length of 5 meters. Okay? Also, we mentioned here that the section itself is made of grade 50, and we are given the specific section for that I-beam, while the plates themselves, they are made of 350W grade steel, and we are given the dimensions of the plate. So when it is mentioned 300 by 20, it is obviously that this dimension is 300 and that thickness is 20 millimeters. Okay? Once we know the cross-sectional area or the name of the listed W section, we can actually grab all the information that we need and we discussed before. We need the area, Ix, Iy, depth, width, breadth, and thickness of the flange, as well as the J and the CW. All these values we were required during the example to evaluate the compressive capacity of that very beam. Okay? So we need to evaluate the capacity. The first thing is to know whether we can just use the CR equation as is, or we need to consider local buckling. So we have to check local buckling. So we will start by checking the local buckling. We will start with the web, and the web doesn't have any plates, so we can just go ahead and check it similar to what we have done in the previous 3 examples. So we evaluate the limit for the web, which is 670 divided by the square root of F yield, and we divide D minus 2T by the W and compare the two values, and if the slenderness of the web does not exceed the limit for the web, then the web will not encounter any local buckling. So no local buckling will occur in the web. Now we need to check the flange, and I already gave you a note that flanges are stiffened by the plates, so we need to check the limit for the plates, not for the flanges. Remember that the limit for the flanges was 200 divided by the square root of F yield. But now, since we are checking for the plates, the limit for the plate is actually 670 divided by the square root of F yield. So if we went to table 1, we can actually see that limit. So the limit will be slightly different from the one that we used for the web, because we have different grade of steel between the section itself and the plate. So we can evaluate that limit. And also we check the slenderness of the plate, which is 300 divided by 20, because the plate can buckle with its full length. So if this plate is to buckle, it will just look like that. That's why we divide the entire B divided by T, and this will give us 15. It is lower than the limit for the plate. So there will be no local buckling in the flange nor the web. That means that the section as a whole satisfies table 1, and we can use this equation as is without any problem. This section is doubly symmetric, about x and y axes. So FE will be the minimum of FEX and FEY and FEZ. All the remaining parts in this example will be similar to the previous example, except for one aspect where we need, or actually two, where we need to check the updated section properties, areas, inertias, and Rx and Ry for the combined section. And the second thing is the buckling length in the Y. It will be shortened due to the lateral support. So we need to check the properties of the built-up section. So areas and inertias. We will start with the areas, which are easy. You will just add the area of the I-beam, and you will add 2 multiplied by the area of the plates, and because we have 2 of the plates, one in the top one and one in the bottom, so we will get the full area of the built-up section. Now we need to check the inertia, the combined inertia of the built-up section. Remember, in the old times we have the concept of axis transfer, where you have the entire combined axes for the entire section, and we have some local axes for each of those areas that are creating this section. So for the I-beam, you will just put it as is, because the axes of the, or the local axes of the I-beam itself coincide with the centroid of the built-up section as a whole because of symmetry. But for those local x-axes, they need to be transferred. How they will be transferred? It is the area multiplied by the distance between the local axes to the global axes. So this is literally it. You will have, of course, that will be added to the original inertia. So we will start with the original inertia, which is BH cubed divided by 12. And I encourage you to write this down if you just need to remember the formula, and the formula in the steel book as well, right after the structural tables. And you add to that the area of the plate, and that is simply the distance between the local axes and the global axes, and you square that. So those are just some geometry playing. And don't forget to multiply this by 2, because we have 2 plates. Now, instead of just having the inertia of the I-beam, we have a larger inertia of the combined section. Okay? We will do the same very thing for the y-axis, but it is much easier, because the local axes of all of the sections are coinciding. They are all along the y-axis, so we don't have any problem. So we will just add the inertia of the I-beam plus 2 multiplied by the inertia of the plate. And keep in mind that BH cubed divided by 12 will be reversed in that case, because we usually multiply the dimension that is parallel to the axes multiplied by the cube of the dimension that is perpendicular to the axes. Now we have an updated inertia in the y-axis as well, and simply we can just evaluate the radius of gyration of the built-up section. So you'll just have the inertia divided by the combined area, and you will update the R naught bar squared, because it is literally the addition of the squares of the 2 Rx squared plus Ry squared. Okay? Once we made this, which is the hardest part of this example, is just to find the properties of the built-up section. Everything else is just almost identical to the previous example. So you will find me going a little bit faster in the following part because we literally did that before. Okay? So we will start by calculating FEX, FEY, and FEZ because FE, it is just the minimum of those two values. So we have the equation of FEX, which is pi squared multiplied by E divided by KL over R all squared. So we have the pi, the modulus of elasticity of the steel, which is a constant equal to 2 by 10 to the power 5. K is equal to 1 because we have a pinned column. One thing I will probably need to emphasize on, it is actually the buckling length. We will find that the buckling length in the x-axis will be the full length. We discussed this earlier. While the buckling length in the y-axis, it will be the half of the length due to the beam in the middle. And we will use the radius of gyration that we just evaluated for the combined section and crunch those numbers together to get the FEX value. Exactly similarly for the FEY, everything is identical except for the buckling length and the RY. And you will get yourself the new FEY. Okay? Once we have the FEX and the FEY, in that case, we still need the FEZ to compare it to the three values, and FE will just be the minimum of the three values. As usual, FEZ, it is a lengthier calculation, but hopefully easy. So we have the pi squared, E constant, CW, it is just the CW that we extracted from the tables because we mentioned that the built-up section, we assumed that will not significantly influence the CW and the J values. KZ is equal to 1, not because of that it is pinned, but it is always equal to 1 based on the code. And the buckling length will be the full length, and this is always the case because we assume that usually intermediate beams will not limit the rotation about z-axis of the column. And then we have the shear modulus, 77,000. This is a constant as well. This is the value that we extracted from the table. And we have the area of the combined section. Don't forget about this because it is by adding both areas together. That is what we got over here. And we have the updated R node bar squared that we evaluated earlier by adding the Rx squared to the Ry squared. Then we have the FE set. We compare this to this to this, and we will find that the minimum of them is actually this value. So this will be the value that we will use in the evaluation of lambda, and then the CR. And that's exactly what we will do in the next slide. You divide F yield by the FE that you evaluated from the previous slide under the square root, and you got the lambda. And since we have a hot rolled section and it is a doubly symmetric section, even that it is slightly built up, but we can still use the N, but we mean by the built up section when the section itself is made of a couple of plates. Only in that case, N will be equal to the 2.24 that is mentioned in the code. Then we will just use the lambda. We have the area of the built-up section that we evaluated over here. And everything else is just very clear. Someone can ask me, why did we use the F yield of the I-beam, which is the hot rolled section, not for the plates? First, because the plates are minimal area compared to the I-beam, and also we are going into the conservative side. If you would like to be very accurate in that, you should be doing a weighted average. So you multiply the area of the I-beam multiplied by the F yield of the I-beam plus the area of the plates multiplied by the F yield of the plates. In that case, you will be more accurate, but just for simplicity, we multiplied it by the lower F yield, and it happened to be the F yield of the I-beam. Okay. In that case, we found that this column can resist around 15,500 kilonewtons. Okay. We will solve another example that talks about what if the section does not satisfy table 1. So that will be according to this very clause, that if the section does not satisfy table 1, so exceeds the thickness, the width or diameter to thickness ratios of table 1, in that case, so table 1 is not satisfied. So we need to either go with the effective area. I know the font is very small here, but luckily we are recording this lecture. And we will use just the regular F yield, or we use an effective F yield in our equations. So if you have a section, let's say an unequal angle like that, probably the buckling will happen in the longer leg. So you have one of two options. Either to assume that, you know what, we're not going to use the entire length of the section. We will just use a reduced section and a smaller area. So you will ignore this part. So in that case, you are working with an effective area. You are using an effective area. And that effective area will only be used in that very equation. Everywhere else, it is not included. Or we know what we will say, you know what? We will exhibit local buckling if we reach the maximum yielding capacity. So alternatively, I will use the entire section, even with this additional part. But instead of going to the entire F yield, I will not reach the entire F yield. I will reach a lower part of it. A lower part of it. So there are two different approaches, and it is worth mentioning that they may not give the same exact results. So one of them is assuming that we will use a smaller cross-section area by ignoring part of the area, and the other will assume that we will use a reduced value of the effective F yield. How can we get the effective area or the effective yield? This is what I will going to show you in the next example. So it is literally from the equation of the from equations of table 1. So let's say if you have d minus 2t divided by w is equal to, or it has to be less than or equal to 670 divided by the square root of F yield. Let me double check. Yes. So one of the ways is to consider this depth as an unknown and assume the yield, assume the 670, and we know the W, and you will have a smaller depth, and that will be the one that will dictate the smaller area. Or we will say, you know what, let's just keep everything, the cross-section as is, and consider the F yield is a reduced F yield. So you will consider this to be unknown. And this is the one that I believe it will be easier for students, that you will just reduce the F yield to a lower value called effective yield stress. Once you evaluate that, this is what you are going to use in that equation and in that equation, and just find the capacity of the compressive member based on that. Okay? So let's just see the example and solve it. I already talked about the shear center. Since we will solve an angle, so I'm just refreshing your mind that the shear center of angles, it is at the intersection of the two legs. So if you have an angle like that, this is where the shear center is. And it is worth mentioning that there are some tables for double angles. If you have two angles back to back, you have tables for that to get the properties from. And this is what we are going to use in the next example. And those values depend on the distances between those two plates, or between those two angles, because you will put a plate in the middle, and obviously the more you increase this spacing, you will increase IY. This is why they differ. Okay? So we have this example. We are required to evaluate the compressive strength of this column. And we are given that the column has a length of 400 millimeters. There is no lateral support along the entire height. We have pinned column, so in that case K is equal to 1. And we are given the distance between the two angles and the naming of the angle. And for the very first time, we have the grade to be a different value. We have grade 300W, which is lower than the one that we used in the previous examples of 35 megapascal. We have 300 now megapascal. And we went to the tables of the single angle to get all these dimensions or those properties from the tables of a single angle. And based on that, we can just go and check the local buckling. We started with the smaller leg, which is L1, and we evaluated the limit, and we found that there is no problem at the shorter no problem at the longer leg, but this one does not satisfy the local buckling. That means that the slenderness of this leg is higher than the limit. So this is the shape of our angle. So why don't we assume that, I'm so much exaggerating, so why don't we assume that this part is not part of the section? This way, as if we are asking ourselves what will be the longest length where it will still be safe for local buckling. And that's exactly what we did. So we assume the dimension of D dash that will be taken out of the angle, and the only unknown by saying that the buckling slenderness equal to the limit. So we put all the dimensions, and the only unknown is D dash. So D minus D dash, we know the depth, the original one, but this one, we still don't know how much we need to cut from the angle. So if we substitute in this equation, the only unknown that we'll find is D dash. So we found that it is equal to 40.4, which means if we cut a length of 40.4 millimeters, this section would have been satisfying the local buckling. So let's just go ahead and evaluate the area of the remaining part. As if we just have this area that is hatched in red. So you will just have the original area subtracted from the area that you are going to delete. So you will get an updated area. Now you can just proceed and solve the example similar to any easier previous example. So you have the equation, and since this section is only singly symmetric, so it is symmetric about only y-axis, so the FE is the minimum of FEX and FEYZ. So you evaluate FEX and you evaluate FEY because you need FEY to evaluate FEYZ. And FEYZ will be function in FEY and FEZ. So we need to evaluate FEZ as well. And we talked about those values that we are going to extract from the tables of double angles. So we have the Rx squared and the Ry squared. That shouldn't be a problem. The only new thing now is that we have a distance between the centroid and the shear center. And this distance we will find from the table equal to 55.4. That's only for the y node squared. Or the y node, I mean. X node, they are identical. There is no shifting in the x-axis. Once we have the r node squared, we can just use this value to substitute in the FEZ equation. It is worth mentioning, and it is now, keep in mind that it is a confusing part, that the area that we used in this equation, it is just the full area. So the only time that we will use this updated effective area is in the CR equation, in the compressive strength equation. Everywhere else, you will just use the regular area. Okay? So you have the FEZ. You can now evaluate the FEYZ. That is function in epsilon. And we already evaluated FEY and FEZ from previous calculations. Sorry, not epsilon, omega. Omega is equal to 1 plus x node plus y node plus r node bar squared. So x node square plus y node square divided by the square root of r node square. You may find a slight difference between version 11 and version 12 in that very equation. But even if they are different, you will find that they are providing the same exact value. So you don't need to worry about anything here. So if you noticed some differences, it is just a rearrangement of the equation. All these values we already know. So the x node is equal to 0, y node is equal to 55.44, and r node squared, we evaluated this before, so we will get the omega. We will use that to calculate the FEYZ. Now we have the two values that we need to compare, which are the FEYZ as well as the FEX. We will compare those two values and the minimum will govern the capacity. We will find that this one actually governs the capacity. So we will use that to calculate lambda. And don't forget that this is actually the area that you are going to use, which is the effective area, while taking out this additional part. Okay? I also solved the same exact example by working with the effective yield stress, not the area. And you'll find that nothing will actually change except for the calculation of the CR. So FEX, FEY, FEZ, all those calculations will just remain the same except for the substitution of the lambda and the CR. And that's exactly what we have in this other option B. So you will put the length of the leg divided by the thickness of the leg, and you will put the equation for the limit, which is 250 divided by the square root of F yield. But in that case, it will not be just F yield, it will be the effective yield stress. This is the only unknown in the example, so you can just go ahead and evaluate this unknown. Once you found out what is the value for this unknown, you can just substitute by this effective yield stress in the lambda equation and in the CR equation. And you can just get the CR easier. You still need to calculate, of course, the FE and stuff, but the only difference is instead of just keep on finding what is the reduced area and to find the area, the effective area, and to be confused which area are you going to use in some equations, is it the one, the effective one, or the only area? Here it would be just simple. You use an effective yield stress, and that would be it. Okay. You will find also that CR in that type of calculation is slightly different than this, but even that in this example it is slightly different. In some other examples they are actually significantly different. So both are correct because both are options to be used in the code. But it is up to you which one to use in the exam. Obviously, I prepare the model answer with both answers, and it is up to you which one to use when you solve the example. Okay? I hope that the lecture is clear. I will also go through it when we go in person. If you would like to have questions, please write down any questions that you would like to ask. And yeah, I wish you all the best. Take care.